All right, here comes our second speaker for 14th Geometry Topology Summer School, Jesse Madnick, recently moving from University of Oregon to Seton Hall University. He's going to talk about minimal submanifolds in spheres. It's my pleasure that he's participating as a second time speaker for us.
Yeah, so thanks, Mustafa, for the invitation to speak here. It's a real privilege and certainly a pleasure to share geometry with others. And yeah, I had a great time last time, so thank you very much for having me back.
Welcome.
So yeah, so I'm going to talk about minimal submanifolds in spheres is sort of the theme. The plan is to have 4 lectures. The first lecture today will be about setting foundations. So this is meant to be very basic. This is an introductory lecture. If you're an expert in minimal submanifold theory, this might not be the most interesting for you. Sorry about that. This is meant to be introductory, just so that we're all very much on the same page. So I'm going to talk about minimal submanifolds. I'm going to talk about stability and this notion of the Morse index and nullity. And then at the end of this lecture, we'll talk about calibrations. There might be some overlap with what Federico Trinca mentioned, but maybe our perspectives are slightly different given the applications. But of course, a little bit of repetition in an introductory course couldn't hurt, I think. Then in tomorrow's lecture, we're going to specialize to submanifolds of the round sphere. And I want to talk about a class, or really several classes of submanifolds in the round sphere that collectively fall under the heading of semi-calibrated submanifolds. The material in tomorrow's lecture, lecture 2, is technically standard, but I hesitate to call it well known. It's sort of scattered throughout various papers in the literature. And this is really something I'd kind of meant to write maybe a survey article about for a while, but just never got around to it, because there is sort of a, I wouldn't say a unified way, but many sort of classes of submanifolds that appear in spheres which maybe look different are in fact very similar to each other. And there's a reason that many different classes of submanifolds which seem similar, they are in fact similar. So we'll talk about that tomorrow. It's mostly standard stuff, but maybe, sort of scattered throughout the literature. Then in the last 2 lectures, I'll talk about joint work with Gavin Ball and Uwe Semmelmann on isoparametric hypersurfaces in round spheres. So in lectures 3 and 4, we'll be in the codimension 1 case. And isoparametric hypersurfaces are really just an incredibly beautiful subject, in my opinion. I only learned about them maybe two or 3 years ago when I embarked on this paper with Gavin and Uwe, and I was really kind of blown away by just the richness of the subject. So I'm excited to share what it is that I've learned with all of you. And still myself, I'm still becoming slowly expert on the isoparametric theory, but there's a lot that certainly many folks know that I don't. As for the sort of dependence of the lectures, this is sort of the flow chart here. Lecture 2 tomorrow is actually independent of 3 and 4. So if you find tomorrow's lecture, which is a bit technical in certain places to be overly technical, that's okay. You can come back in lecture 3 and be able to follow along, no problem. But both lectures 2 and 3 rely on 1. And again, lectures 3 and 4, I have to emphasize, are joint work with Gavin and Uwe. Gavin has also moved. Gavin will be starting at the University of Missouri. Okay, so let's set foundations. Let's talk about our objects of interest. So we're interested in submanifolds. So for most of this talk, M will denote a Riemannian manifold of dimension n plus k. N is at least 2 and k is at least 1. Nabla bar will be the Levi-Civita connection on M. And we're going to be interested in n-dimensional submanifolds in M n plus k. Okay, so n is the dimension of the submanifold and k is the codimension. Okay, in general, I'm going to be a bit vague as to whether these submanifolds are immersed or embedded. Most things I'm going to say won't make a difference. When it does make a difference, I'll point it out. So we're really interested in the extrinsic geometry of submanifolds. And the extrinsic geometry is governed by the second fundamental form. Okay, so this is a symmetric bilinear form with values in the normal bundle. Okay, you take the covariant derivative of x with respect to y, and you project onto the normal space. Okay, it doesn't look like this is symmetric, but one of the things you learn in a Riemannian geometry course is that this is in fact a symmetric bilinear form. And this is, in a sense, a complete local invariant. It's a second order local invariant. This really is the fundamental object that gives a submanifold its shape. Now, symmetric bilinear forms, especially those that are not valued in a line bundle, those that are valued in possibly a very high rank vector bundle, these can be complicated objects. And so you would like to summarize some of this information, and you can do that by, for example, taking a trace. When you take the trace, you get a normal vector field called the mean curvature. Okay, and we'll discuss the geometric meaning of the mean curvature in a minute. And in general, in differential geometry, whether you've seen a, when you see a tensor or some sort of object for the first time, I think a good impulse is to ask, can I decompose it into irreducible pieces, right? So if you're learning about the Riemann curvature tensor for the first time, you say, wow, what a scary object. But then you say, well, maybe I can decompose it into irreducible pieces, and that gets me the Ricci, traceless Ricci scalar and Weyl curvatures. Because otherwise, how do you know whether, by taking the trace, for example, you get all there is to know, all there is to be gotten. Maybe there are other contractions of the second fundamental form. Maybe there are other combinations that give you interesting things. But it turns out that when you decompose the second fundamental form into O of n irreducible pieces, you absent extra structure, assuming there's no extra structure, you only get these two. You only get the traceless part. That's Roman numeral 2 subscript 0 defined by that formula, and the mean curvature. So in a sense, this is sort of all there is to be gotten, absent extra structure. There's the mean curvature, and then there's the traceless part. Okay, the mean curvature, as I'll explain in a minute, is deeply tied up with area. I'm going to use area to refer to the area of the submanifold, although I think later in the talk I might switch to volume. Okay, well, we'll say that a submanifold sigma is area minimizing. Here I mean homologically area minimizing if the following is true. If for all compact subdomains K in sigma, we require that the area of K is less than or equal to the area of any competitor, where a competitor is a compact subdomain in M, not necessarily in sigma, but it has the same boundary. Okay, so it's homologous. Oh, that K prime should be K tilde, sorry. That K prime obviously should be K tilde, that's a typo. Okay, so if you have a submanifold, you might want to know, how can I check if it's if it's area minimizing? How would I actually check this condition in practice? And in practice, as we'll see, it really is quite hard. Later in the talk, we'll develop sufficient conditions. But before we develop sufficient conditions, let's first notice the following obvious necessary condition from calculus, which is that if you have a local minimum of a function, then necessarily the first derivative of that function at that point is 0. So inspired by this, we make the following definition. A variation of sigma is a family of, let's say, immersions, iota sub t. This is a one parameter family. T ranges in negative epsilon epsilon. And iota sub 0 is the immersion, or embedding that you started with. And iota sub t has to agree with iota outside of some compact set. So we'll say that sigma is a minimal submanifold if the area of iota sub t of sigma is the derivative of the area of iota sub t of sigma is 0 at time 0 for all variations. Okay, so by our calculus remark, every area minimizing submanifold is necessarily minimal. Okay, so minimal is sort of a strange name when you think about it. All we're requiring is that the first derivative of area be 0. We're not saying anything about the second derivative, right? Minimality is somehow, maybe we should have called them critical surfaces or something, or stationary surfaces as they're called in the geometric measure theory literature, but we're sort of stuck with this name. Okay, so when you have a variation, you can write down this variation vector field eta. Okay, so that's somehow the direction in which the variation is happening. And using this, you can derive this very famous formula. This is the first variation of area. And this gives us a geometric interpretation of what the mean curvature is. It also gives us a criterion. This gives us a way of checking whether or not a submanifold is actually minimal, right? So from this formula, the first variation of area, together with some, the fundamental lemma of calculus of variations, we see that a submanifold is minimal if and only if its mean curvature vector field is 0, right? And that obviously is a, often an easier condition to work with in a sense than the actual minimality condition, which is a variational condition. You certainly don't want to check that the derivative at time 0 of the area of iota sub t of sigma is 0 for all the, for all the infinite dimensional space of variations. You'd rather check, you'd rather compute the mean curvature and see whether it's 0, of course, right? H equals 0 is a checkable condition. But it's worth asking, what sort of a condition is it, right? What really is H equals 0 at the end of the day when you unwind all of the abstraction? What it is a second order nonlinear PDE system. Okay, it's a second order nonlinear PDE system, and it consists of k equations for n plus k functions of n variables. So that's rather formidable. And that tells us, without knowing anything else, that constructing examples of minimal submanifolds is not going to be so easy. And that studying minimal submanifolds is going to be, a rich and challenging subject, because our knowledge of second order nonlinear PDE systems at the moment is, it's quite limited, relatively speaking. But we notice already from this that there's a sort of trichotomy that emerges. And I think this trichotomy is very important as a way of conceptualizing, well, what's going on when you have a minimal submanifold. So one option is that k is 1. Okay, so when k is 1, your submanifold has codimension 1. It's called a hypersurface. In this case, the equation h equals 0 is just one equation. So your PDE system is just a single PDE. And in this context, you can use PDE methods. The fact is that we understand scalar PDE far better than we understand PDE systems. And indeed, the k equals 1 case is the setting that receives the most attention. It is the setting that at the moment, humans, mathematicians understand the best. We know far more about the k equals 1 setting than we do about the high codimension setting when k is at least 2. Another special case comes to mind. That's the other extreme case. Notice that we're assuming n is at least 2 and k is at least 1. So the other extreme case is that when n is 2. In this case, your minimal submanifold is amenable to techniques from complex analysis. It is quite striking how effective complex analytic methods are, even in high codimension. Many authors have remarked on this, sort of that the relationship between minimal surface theory and complex function theory is somehow mysterious. There are other quotes, I think, from Chern about this. Even continuing into today, there are many spectacular results about minimal surface theory in the n equals 2 case that are proved by using sometimes very sophisticated ideas from complex analysis. It's a really beautiful relationship, in my opinion. Okay, so k equals 1 can be treated by PDE methods, n equals 2 can be treated with complex analysis. What does that leave? Oh, well, only every other case. And so when n is strictly bigger than 2 and k is strictly bigger than 1, this is very hard, and our knowledge at the moment is relatively limited compared with the other 2 cases. Of course, there's been a lot that's written, and certainly there's, there are many things that we know, but we are in many ways far from having a systematic understanding in the setting when n is greater than 2 and k is greater than 1. Many things that are true for n equals 2 and k are equal to 1 are just simply not true in general. Somehow when n is 2 and k equals 1, that's really somehow not representative necessarily of the general case of high dimension and high codimension. So I'll return to this throughout the talk just to illustrate this dichotomy, because it is, or trichotomy really, because this is quite fundamental. Just for illustration, of course, ultimately we'll be interested in round spheres in this lecture series, but I do want to talk for a minute about the situation in Euclidean space, because of course that's the classical situation. That's where we have a lot of our geometric intuition, and a lot of motivation comes from there. So, you might, so far I haven't given you any examples. You might want to construct examples of minimal surfaces. Maybe, you say, I just want to come up with some simple examples in R3. How hard could that be? Maybe I'll assume that my surface is a graph. I'll just go about constructing some examples. So I take a function u with domain omega in R2, it goes to R, and I consider its graph. This is a surface in R3. And I ask, what's the condition for this graph to be a minimal surface? Well, I need the mean curvature to be 0, and that's equivalent to this second order nonlinear PDE here. And already you see that, okay, this really is somewhat complicated. Maybe I'm not going to be able to just solve this nonlinear PDE by eyeballing it. This is really going to be a bit tricky. One indication of just how sort of subtle this is going to be is, you might say, well, maybe my life will be easier if I assume the domain of U is all of R2. But no, somehow that makes matters worse. It's a very influential theorem of Bernstein, which I'll return to later, that if you have a minimal graph in R3 and it's entire, meaning that the domain is all of R2, then in fact the graph of U is a plane. So you won't get any interesting examples if the domain is all of R2. This should be compared with Liouville's theorem from complex analysis. This is, in a sense, a nonlinear analog of that. Okay, but let me give you some examples. Okay, of course, planes are minimal surfaces. What else? So historically, the first minimal surfaces to be discovered are these two. These are the catenoid and the helicoid. And these can be discovered sort of in modern, from a modern point of view by imposing certain geometric ansatses, right? So for example, you might say, okay, the minimal surface system is really complicated, but maybe I can find those that are invariant under the action of some group. So you're in R3 and you look for those minimal surfaces that are rotationally invariant. And you think, surely I'm going to get a lot of these things, but it turns out, no, you only get the plane and the catenoid. This is already an indication, again, of just how somehow difficult this is going to be to construct examples. While it's a beautiful fact that the only rotationally symmetric minimal surfaces in R3 are the plane and the catenoid, in a sense, it's also a bit disappointing. It means that this is really going to be quite hard. So then you say, okay, well, maybe my submanifold, I can put a different geometric ansatz. Maybe I can assume that it's ruled by lines. Maybe that will get me lots of examples, but no, that will only get you the plane and the helicoid. There are only two minimal surfaces in R3 that are ruled by lines. Interestingly, if you ask for ruled by circles, you will in fact get many more examples, which I'll show you in a minute. So if you ask for your minimal surface to be ruled by circles, you can get, for example, this Riemann staircase on the left. Here, I should say, you might notice the years of these things are, it's almost 100 years later. For quite some time, the only minimal surfaces that were known were the plane, the catenoid, and the helicoid, because of how hard they are to find. But then in the 1800s, geometers found many, many more minimal surfaces in R3 using, for example, complex analysis. So the Riemann staircase is on the left. You'll notice that it has infinite topology. It has infinitely many necks. The necks kind of look like catenoids, and that's true in a certain sense. They are sort of catenoidal. And on the right, we have Enneper surface. Enneper surface is very simple algebraically, relatively speaking. And Enneper surface has the funny feature that it's not embedded, it's immersed. You can't quite see that from this picture, but if you were to zoom out, you'd notice that the sort of top two lobes intersect each other here, and the bottom two lobes intersect each other there. So here we have an example on the left of a minimal surface with infinite topology, and on the right, a minimal surface with self-intersections. And amusingly, quite strikingly, in fact, for 200 years, no one could find a complete minimal surface in R3 that was embedded and had finite topology. Right? So all of the examples discovered in the 1800s that were complete either had self-intersections or had infinite topology. So this was this kind of major open question to find a complete minimal surface that was embedded and had finite topology. It took quite some time. But in the 1980s, Costa discovered this surface, which has, I believe, genus 1 and 3 ends. Then its embeddedness was proved by later by Hoffman and Meeks. So this is sometimes called the Costa-Hoffman-Meeks surface. And so this sort of opened up this vista. Suddenly the sort of landscape opened, and folks found ever since 1982, in the last 40 odd years, just dozens and dozens, if not hundreds, of complete embedded minimal surfaces with finite topology. This is sort of now a big industry. But I want to sort of revisit the Bernstein theorem from before about the minimality of entire graphs. We discussed it for surfaces in R3, and I now want to ask, to what extent is the Bernstein theorem for surfaces in R3, is that still true for an n-dimensional minimal graph in Rn plus k? This is somewhat instructive as it illustrates the difference between low codimension and high codimension. So to be precise, let's let n be at least 2, k at least 1. As always, u will be a C2 function from Rn to Rk, and we can look at its graph. This is an n-dimensional submanifold of Rn plus k. We'll say the function u is entire if its domain is Rn. So the very famous and extremely influential, even into today, Bernstein problem asks the following. Does there exist an entire minimal graph in Rn plus k other than the n plane? The answer is extremely striking. When k equals 1, the answer is no, provided that n is at most 7. This is due to a series of papers in the 1960s due to Fleming, De Giorgi, Almgren, and then this was settled. That no direction was settled by Jim Simons in a very famous 1968 paper. But the answer is yes, if n is at least 8. And this was proven shortly thereafter by Bombieri, De Giorgi, and Giusti. They have some example that I embarrassingly don't remember. But there do exist, but the question of whether there exist entire minimal graphs in codimension 1 other than the n plane depends in this very funny way on the dimension. And if you look in the minimal hypersurface literature, you'll often see this exact dichotomy, certain theorems which are true for n at most 7 and fail when n is bigger than 8. This dichotomy in the codimension 1 case happens again and again for, there are reasons for this. So then you might ask, okay, well, what about in high codimension? Interestingly, in high codimension, the answer is just an unqualified yes. It doesn't matter what the dimension is. There are certainly many entire minimal graphs other than the n plane in high codimension. And one way to see that is to use Werdinger's theorem. Werdinger's theorem is quite old, and it's an extremely beautiful theorem. It goes like this: every complex variety, I suppose I should say smooth, but every complex variety in Cn is not just a minimal surface, minimal submanifold, but is in fact area minimizing. This really is kind of an amazing fact that ties somehow the algebra of complex numbers and algebraic geometry and relates it to differential geometry and the study of area. It's an amazing thing that complex varieties are area minimizing. Here I should say that real varieties need not be area minimizing. Real varieties need not be minimal surfaces even. So Werdinger's theorem is somehow very surprising and very deep and beautiful, and we'll come back to it several times. In particular, Werdinger's theorem gives us, just uncountably many examples of entire minimal graphs other than the n plane in high codimension when k is at least 2. Okay, so this again illustrates this dichotomy. Okay, so I want to move on and start discussing one of the quantities that we'll be interested in, which is the Morse index. So going back to this question of how can you tell whether a surface is area minimizing, right? We didn't really answer that. We gave a necessary condition earlier in the talk. And when we gave that necessary condition, we used calculus. We recalled that if a is a local minimum of a function, then the first derivative is 0. But of course, there's another necessary condition from calculus, and that's that the second derivative be non-negative. We forgot that. So we can make the following definition. We can say that a submanifold is stable if, well, we require two things. We require first that the first derivative of area be 0 for all variations at time 0. And also we require that the second derivative of area be non-negative for all variations. So from this calculus fact, we see that every area minimizing submanifold is stable. And by how I've defined it, every stable submanifold is minimal. Neither converse is reversible. These converses these inclusions are strict in general. Okay, so again, we should ask for examples. In Euclidean space, we've mentioned a bunch of examples in R3. In Euclidean space, certainly every n-plane is area minimizing and hence stable. And you might ask, what other complete stable submanifolds in Rn plus k are there other than n-planes? Are there any? This leads to the so-called stable Bernstein problem. This is a cousin of the maybe graphical Bernstein problem that I mentioned earlier. The question being this: do there exist complete two-sided stable immersions, or if you like, do there exist complete two-sided stable immersions other than the n-plane? Here by two-sided, I mean that the normal bundle is trivial. Okay, so this is a very famous question. And again, we'll see this split between the low codimension and high codimension case. So when k equals 1, if you're in codimension 1, the answer is no if n is at most 5. This is due to very recent work this year. So people have been pushing up this number n for over the course of many years. There's a long history to this. But at the moment, results of Chodosh, Lee, Minter, and Stryker and Mazet say no when n is at most 5. The answer is yes when n is at least 8 by the theorem mentioned earlier of Bombieri, De Giusti, and Giorgi. This is a corollary. And as far as I know, this is an open question when n is 6 or 7. I expect that the expectation is that the answer will be no for n equals 6 or 7, but at the moment, we don't know one way or the other. This situation, again, is radically different in high codimension. Do there exist complete two-sided stable immersions other than the n-plane in high codimension? Yes, again, by Verdinger's theorem. You just take your favorite complex variety. So, I mean, one thing to point out here is that, at least in the codimension 1 case, stable minimal submanifolds in codimension 1 and low dimensions are clearly quite rare. They're only n-planes. And in general, we sort of expect that stable submanifolds are, in a sense, very rare and hard to come by. That is especially true when the ambient space is positively curved in some sense. When the ambient space is positively curved or has some amount of some non-negative curvature or something, you maybe hope that you can classify the stable submanifolds. So for example, in the round sphere, so that's the sphere with the standard round metric, it's a famous theorem of Jim Simons that every minimal submanifold is unstable. So there is not a single stable minimal submanifold to be found. You might ask whether that's still true if the metric is close to the round metric. There's a lot of research in that direction. And one of the motivating kind of questions is this so-called Lawson-Simons conjecture, which is still open. If the n sphere is equipped not with the round metric necessarily, but with some quarter pinch metric, is it still the case that every minimal submanifold in the sphere with that metric is unstable? This is an open question. There's been a lot of work on this. I'm not an expert, but there's been, I know, a lot of work on this, partial results. The previous speaker, Federico Trinca, for example, has work in this direction. So there's been some progress here. But getting back to sort of the compact rank 1 symmetric spaces, you might ask again, well, okay, there are no stable minimal submanifolds in the round sphere. What about in CPN? A famous theorem of Lawson and Simon say that there are, in fact, stable submanifolds in CPN. They're exactly the complex submanifolds. You can ask a similar question in HPN and OP2. And again, somehow the stable submanifolds are extremely rare. In the quaternionic case, they have to be quaternionic, and in the octonionic case, they have to be octonionic. And those submanifolds, by the way, are extremely rare. Quaternionic submanifolds of HPN, I believe, have to be totally geodesic. I don't remember the status of octonionic submanifolds in OP2, but if I were to guess, those are probably totally geodesic as well, but don't quote me on that. Okay, so when the ambient space has some non-negative curvature, you sort of don't expect there to be many stable submanifolds. Maybe you even hope to classify them.
Yes.
So that means that if
it's in Lawson-Simon's conjecture, the metric has a Ricci curvature positive.
Yes, yeah. When I say quarter pinched, I mean positive sectional curvature and quarter pinched. Yeah.
Ricci curvature. Already positive. Okay.
Sectional. Yeah. Sorry, when I say quarter pinched, that's what I mean by that. Yeah.
Okay. All right. Then another one is like in this Lawson-Simon's theorem is, as far as I see, complex submanifolds are stable is Simon's result, and the other direction is by Lawson, you mean?
No, there's a paper of the two of them. There's a paper that the two of them wrote.
Oh, okay.
Together. Yeah. There's a 1973 paper that they both wrote.
Yeah.
That
if it's stable,
sort
then
of
it has to be complex. Okay.
Yeah, exactly. Yeah. The forward direction is the hard part. Yeah.
Right.
The converse is by Vertinger. Yeah.
Interesting. Yeah. Thank you.
Sure. Right. Yeah. So if you So one lesson from these theorems is that, right, if you take a minimal submanifold at random, it's not going to be stable, right? So that raises the following question: if I have a minimal submanifold, can I measure how far it is from being stable? Can I quantify? If I have an unstable submanifold, can I quantify how far it is from being stable? Can I measure that failure in some sense? And you can do that with a number called the Morse index, which is very fundamental. But to explain it, I need a little bit of preliminaries. So we discussed the first variation of area. There is, of course, also a second variation of area, and presumably a third variation, though I haven't seen that in quite a while. So the second variation formula says this: suppose you have a minimal submanifold, and let's agree to consider just those variations whose variation vector field is normal. So those with a normal variation vector field. Then the second derivative of area of the variation at time t equals 0 is given by this integral that you see here. Okay, now what are these terms on the right-hand side? So the first term, delta perp, this is the connection Laplacian associated to the normal connection. Okay, that's a second order operator. And then B is a 0th order term coming from the second fundamental form. Here I'm summing on I and J. And then R is also a 0th order term coming from the ambient curvature. And here EI is a local orthonormal frame. So the point is that the second derivative of area, which of course controls stability, is in turn controlled by this integral. And the operator that appears in this integral is sufficiently fundamental that it gets a name, and this name is the Jacobi operator. Oh, I should say that sign conventions vary. Different people have different sign conventions, which is extremely confusing. It's confusing to no end, but these are my sign conventions, okay? So the Jacobi operator of sigma is the second order linear differential operator that appears in this integral. Okay, so once again, it has this second order term given by the connection Laplacian, and then these 0th order terms, B and R. So the point is that the stability is completely tied up, is completely encoded by this operator here. So it's of fundamental interest to understand this second order linear differential operator as it completely encodes the stability. And my notation is that this, we'll remember that delta squared A of eta means this. Okay, so in the case where sigma is compact, of course that can't happen in Euclidean space by the maximum principle, but in the case where sigma is compact, then this operator is a strongly elliptic operator, and we know from the theory of those things that the eigenvalues of J sigma form an increasing sequence of real numbers with finite multiplicities. These multiplicities could be 0. Okay, so there might not be any negative eigenvalues, for instance, but yeah, the eigenvalues at least are real, and they form this increasing sequence of real numbers going to infinity. And so together, these eigenvalues and their multiplicities are together known as the Jacobi spectrum. And the Jacobi spectrum is a very fundamental invariant of your minimal submanifold. And using these numbers, you can construct further invariants that are maybe more famous, such as the Morse index and the nullity. So the Morse index, roughly speaking, is in a sense the number of, I mean, very intuitively, it's the number of ways you can deform your minimal submanifold to shrink its area to second order. And the nullity is the number of ways you can deform your minimal submanifold to keep it minimal, again, to second order. So more precisely, it's the maximum dimension of space of infinitesimal normal variations on which the second variation is negative definite or 0 respectively. But the way you calculate it is by adding up the multiplicities corresponding to the negative Jacobi eigenvalues. That gets you the index. And then the multiplicity of the 0th eigenvalue gets you the nullity. Okay, so given a minimal submanifold, this is, these are really fundamental numbers. And the index in particular is the obstruction to being stable. The index is 0 precisely when your submanifold is stable. A very hard problem is this, given a submanifold, we want to, of course, calculate the index and calculate the nullity, as I'll, we'll come back to this point several times, but this is really extremely hard. This is just simply extremely hard because calculating the eigenvalues of a Laplacian is very hard, and this is somehow even worse because you have these 0th order terms. You're working with the Laplacian on the normal bundle. So in general, calculating the index and nullity is really kind of hopeless. This is maybe only really doable in extremely special cases. So what geometric analysts tend to do instead is they prove estimates. Okay, so what geometric analysts do is they prove estimates that relate the index and nullity to more familiar quantities such as the curvature and the area and especially the topology. And there are many conjectures, especially in codimension 1 and low dimensions, relating the index to the topology and that sort of thing. So this is sort of a big question. Nevertheless, and one more thing I should say is that in a sense, the index is often somehow a measure of simplicity of the submanifold. I'll return to this later. But the philosophy is, roughly speaking, that somehow the quote unquote simpler your minimal submanifold is, the lower the Morse index should be. And so if you fix the ambient space, like say the round sphere or CPN, you often hope to maybe even classify those submanifolds, which are not only stable, which have index 0, but maybe you hope to classify those of index 1, those of index 2, etc. Those of index equals a small number, because those minimal submanifolds are somehow relatively simple. And indeed, it seems to be the case that minimal submanifolds with a high degree of symmetry, the ones with a high degree of symmetry seem to have low Morse index and nullity, relatively speaking. That seems to be a theme. So just by way of illustration, let me just mention some Morse indices in the case of R3. Okay, so here I'm, I should say that the previous slide is really relevant when sigma is compact. In R3, there are no compact minimal surfaces, but nevertheless, for non-compact minimal surfaces, you can still define the index and nullity by taking exhaustions. Let me not go into how that works. But okay, I mean, the index and nullity makes sense. This is only for this slide that I need the index and nullity of non-compact submanifolds. So one can show people have shown that, for example, the plane has index 0, the catenoid and Enneper surface mentioned earlier have index 1, the Costa surface has index 5, and the helicoid and Riemann staircase have infinite Morse index. And it's a theorem of Lopez and Roos that, in fact, the only minimal surface in our complete minimal surface in R3 with index 1, the only ones are the catenoid and the Enneper surface. So looking at this list, of Morse indices, you might notice that there's this funny gap from 1 to 5, and you might wonder what's happening there. Folks have noticed this gap for a while, and fairly recently, Chodash and Maximo in a couple of papers, they showed that, well, in one paper, they showed that there are, in fact, no immersed minimal surfaces in R3 of index 2. Moreover, there are no embedded minimal surfaces in R3 with index 3. I believe that there are immersed ones, if I recall correctly. And they managed to prove this very nice relationship between the index and the topology. So if you have a complete embedded minimal surface in R3 with genus G and R ends, then the index is at most that number there, 1/3 times 2G plus 4R minus 5. So again, this is sort of an illustration of how the topology can control the index. Open problems in R3. There are still many, amazingly, there are still many things we do not know about minimal surfaces in R3. So for example, we don't know whether there exists an embedded minimal surface in R3 with index 4. I think it's expected that there isn't one, but that's not known one way or the other. It's also hoped that we could maybe classify the embedded minimal surface. Again, I always mean the complete embedded minimal surfaces in R3 with index 5. There's the Costa surface, and I believe some of its deformations, maybe your perturbations have index 5 as well, but it's unclear whether those are all of them. Okay, so this is at least a situation in which we can visualize. So I wanted to mention it, but of course, in general, we won't be in Euclidean space. We'll be in other contexts. Okay, so earlier in the talk, we talked about this notion of an area minimizing a submanifold, and we talked about that there are necessary conditions to check whether your submanifold is area minimizing. Necessary conditions are, for example, if it's minimal, or better yet, if it's stable. But maybe you want sufficient conditions to check whether your submanifold is area minimizing. How on earth can you do that? And how did the subject of calibrated geometry come about exactly? So, so a little bit of history that I just find very interesting. So in the 1970s, there was this really wonderful paper of Lawson and Osserman, I think in ACTA. And the thrust of that paper is that, again, there's this huge difference between codimension 1 and the high codimension situation. Lawson and Osserman look at the Dirichlet problem for minimal surfaces in various dimensions and codimensions, and what they show is that there's a really, really huge difference between how the Dirichlet problem for the minimal graph equation works in high codimensions versus low codimension, high dimension even versus low dimension. These numbers somehow really matter in the analysis. And so here's a very funny example which came up in their paper, which ends up being a very illustrative. So let's let H be the standard hop vibration from S3 to S2. This is this is an equivariant hop vibration. That's called H. And so we're going to use H as sort of boundary data in the following way. Let's consider functions from the closed 4-ball into R3. So U is a function from the closed 4-ball into R3, and let R be a positive constant. And we're going to consider the following Dirichlet problem. We want functions U for which the graph is minimal. That's a second order PDE, and we require that the boundary values of U on S3 is this number R, that's a constant R times H. What can you say about this Dirichlet problem? So in this paper, Lawson and Osserman showed quite strikingly that there are numbers delta 2 and delta 1 such that this Dirichlet problem has a solution for all R sufficiently small. That I think was somehow already known and maybe some sort of standard methods. The striking thing is that there's also a number delta 2 such that the Dirichlet problem has no solutions for R bigger than delta 2. So this is sort of held up as an example of how even the Dirichlet problem, which we think of as being, often fairly well behaved, relatively speaking, is actually, somehow bad in high dimension and high codimension in the sense that you can have non-existence, right, for certain continuous boundary data. So this state of affairs led Lawson and Osserman to ask a question, maybe, if there's no solution for small r and if there is a solution for small r and there's no solution for large r, maybe there's some threshold at which you get a singular solution, right? This is the type of reasoning which is used a lot in minimal submanifold theory, right? This idea that somehow singular solutions live on the boundary of existence and non-existence. So is this the case? Is there some sort of singular minimal graph? And so they hunted for one. They used equivariant methods. And they found this funny function here, which we'll actually revisit next lecture. So let u from R4 to R3 be this function here. You do actually need the root 5/2. As far as I recall, square root of 5/2 times the norm of x times h of x over the norm of x, and u of 0 is 0. So let u be this function. You can take the graph of u, and this is a cone. This is a 4-dimensional cone in R7, now known as the Lawson-Osserman cone. And this Lawson-Osserman cone is the counterexample to certain things that you might hope to be true in high dimension and codimension, but unfortunately are not. So for example, the Lawson-Osserman cone is a solution of the minimal graph equation that is Lipschitz, but not C1. So this dashes hopes for certain types of regularity. Certainly C1 solutions of the minimal graph equation are real analytic by work of Mori, a very old work of Mori, but Lipschitz solutions do not have to be C1. Yeah. So this is sort of an important counterexample to keep in mind, about regularity in high dimension and high codimension. The Lawson-Osserman cone also shows that there can exist minimal cones which are graphical. And at the time, this, I think, came as a bit of a surprise because, there are no n-dimensional graphical minimal cones when n is 2 or 3. And also, there are no graphical minimal cones if k is 1. So this really is somehow a phenomenon that's special to high dimension and high codimension. Okay, so one can check that this Lawson-Osserman cone is minimal, and a question you might have is, given its somehow significance, you might hope that maybe it satisfies something better. Maybe it's stable, maybe even it's area minimizing. So, Lawson and Osserman had this problem, right? They have this great minimal submanifold here, this 4-dimensional submanifold in R7, and how would you check whether or not it's area minimizing? We need some sort of sufficient condition, and thus far we haven't stated any. So the hunt for sufficient conditions to be area minimizing led Harvey and Lawson in 1982 to the definition of a calibration. And really, the inspiration for this definition came from looking at the proof of Werdinger's theorem. Werdinger's theorem, again, saying that complex submanifolds are area minimizing. And what Harvey and Lawson did was they looked at the proof of Werdinger's theorem and sort of in a classic fashion, they took the proof of that theorem and turned the proof into a series of definitions. They abstracted the relevant features of Werdinger's theorem, and the result is that we were given this definition here. So let M be a Riemannian manifold of dimension n, real dimension n plus k. It's a real manifold. A calibration is a differential n form on M satisfying two conditions. First, we require that this n form phi has comass 1. So the maximum value that it can take on orthonormal sets is 1. And second, we require that phi be closed. Okay, And we'll say that an oriented n-dimensional submanifold is phi calibrated or calibrated by phi if phi restricts to be the volume form on sigma. Okay, so this condition is a first order PDE system. It is in fact a nonlinear first order PDE system. Okay, the phi calibrated condition. And the relevance is this. This is sometimes called the fundamental theorem of calibrated geometry. This is what inspired Harvey and Lawson to define calibrations. The theorem is that every phi calibrated submanifold is in fact area minimizing in its homology class. So it's this very famous one-line argument, so to speak, or two-line argument. It goes like this. Suppose sigma is phi calibrated, let K be a compact subdomain, and let K tilde be a competitor, so homologous to K. Then I guess here I'm using volume, I should have used area. Then the volume of K can be computed by the volume integral of the volume form. But since sigma is phi calibrated, the integral of the volume form is the integral of phi. But since phi is closed, using Stokes' theorem, you can relate, the integral of phi on K is equal to the integral of phi on K tilde. K and K tilde are homologous. But then phi has comass 1, so the integral of phi on K tilde is at most the volume form of K tilde on K tilde, that integral, but that's just the volume of K tilde, and that's the proof. Okay, so this shows that phi calibrated submanifolds are in fact area minimizing in their homology class. Right, and so this gives a sufficient condition finally for being area minimizing. I want to point out that this theorem that phi calibrated submanifolds are, for example, minimal, this fits into sort of this general paradigm, which is very important in the study of manifolds with special structure. I'm going to be a bit vague about this, but this falls into the category of what are called first order reductions. So suppose you're interested in a second order operator Q, right? Maybe Q is the, minimal submanifold operator, or the mean curvature operator rather. Sometimes when your manifold or whatever context you're working in, sometimes if there's extra geometric structure, there can exist, if you're lucky, a first order operator P with the feature that the solutions of the PDE for P give you solutions to the PDE for Q. Okay, in this sense, when this happens, we say that we have a first order reduction of the second order differential equation Q. So let me be more concrete. In harmonic analysis, for example, we know that every holomorphic function is harmonic, right? And so this is sort of, in a sense, a linear analog of Vertinger's theorem. Here we have a first order PDE, which is the Cauchy-Riemann equations, implying a second order PDE, namely the Laplace equation. Similarly, sort of a very close analogy is this theorem we just learned, which is that phi calibrated submanifolds are minimal. So on the left, we have a first order PDE, the calibrated condition, and that implies the second order PDE, which is the minimal submanifold equation, right? Mean curvature equals 0. Examples can also be found, for example, in gauge theory on four manifolds. The anti-self dual condition for a connection is a first order PDE, and that implies the Yang-Mills equation, which is a second order PDE for a connection nabla. Okay, and then there are many, many examples beyond these. I guess what I want to emphasize is that somehow these are, this is just somehow a very important philosophy to keep in mind, and a philosophy that's very much going to inform the next lecture, I suppose. And you should sort of hope for these first order reductions, especially when you're working in manifolds with suitable extra geometric structure. Speaking of extra geometric structure, you might ask, where can we get our hands on some calibrations, right? I mean, we've introduced this wonderful concept of a calibration, but this concept is no good if you can't find any. So where can we get examples of calibrations? And it turns out that a very rich source of calibrations come from manifolds that carry extra geometric structure, especially manifolds which have special holonomy. So I'm not going to go into holonomy too much. I don't want to repeat too much of what Federico said. I just want to sort of mention just a little bit for the sake of context. So recall the following. So let's let M be a connected Riemannian manifold. Let's let gamma be a loop at X. Okay, and given this loop gamma, we can consider the parallel translation maps P sub gamma. So P sub gamma takes a vector at X and it parallel translates it around a loop back to where you start. Okay, and what you can do is take all of these parallel translation maps and you can put them together into a set where gamma ranges over all null homotopic loops at X. Okay, and when you do this, you get a set of, well, invertible linear maps, P gamma. And this is called the reduced holonomy group of M at X. Okay, and the word group is okay because this set does in fact form a group. The group operation is loop concatenation. It's a group in the same way that the fundamental group is a group. And also like the fundamental group, the base point doesn't really matter. The reduced holonomy group at different points are in fact conjugate to each other. So we speak of the reduced holonomy group without reference to a point, with the understanding that we really mean somehow subgroup up to conjugacy. Okay, so the picture from Wikipedia is this. You start with this vector here at A, you parallel translate it around this loop, and you don't necessarily get back to where you start, right? So this is an illustration of this P gamma map, parallel translation. Anyway, so the reduced holonomy group is, it's a very important invariant of a Riemannian manifold, and it somehow encodes whether or not your Riemannian manifold admits extra geometric structure. So for example, if the reduced holonomy group is a subgroup of the unitary group, then that tells you that your Riemannian metric is secretly scalar. If it's a subgroup of the compact symplectic group, then in fact your Riemannian metric is secretly hypercalar. So this is not the subject of these lectures. This is, for me, not a lecture series on holonomy. But the point I want to make is that when you have a Riemannian manifold with special holonomy, you in fact get lots of natural calibrations sort of for free. So the big theorem on holonomy is, of course, Berger's list, which gives a classification of the reduced holonomy groups for generic metrics. So what does this say? So when you have a n-dimensional Riemannian manifold, this is capital N. If G is generic, so meaning it's not locally a product and not locally symmetric, then the reduced holonomy group has to be one of these 7 options. Okay, so generically the holonomy is SON, the reduced holonomy is SON, but it could be smaller. It could be U of n over 2, SUN over 2. This can only occur in even dimensions. Could be SPN over 4, SPN over 4, SP1. This only occurs in dimensions that are a multiple of 4. And it could be G2 or spin 7. Okay, I have to point out that when Berger proved this theorem, he didn't know whether all of these cases actually occurred. He just showed that these were sort of necessary. These were sort of the only possibilities. In fact, there was another entry. There was spin 9 on his list, but then later it was shown by, I think, Alexievsky, that spin 9 doesn't actually occur. And it was, with the combined work of many mathematicians over the courses of decades, that it was shown that indeed all of these others do actually occur as the holonomy group of reduced holonomy group of some metric. So one way to think about this list is in terms of norm division algebras, right? In terms of sort of special number systems. In a sense, the ones corresponding to even dimensions, these somehow involve the complex numbers. When you have a manifold with one of these holonomy groups, or even if the holonomy is just contained in one of these groups, you should think of the tangent space as being somehow CM. So not just R2M, but really CM. The tangent space has a complex, an almost complex structure. Similarly, when you're in, when the dimension is a multiple of 4 and you're in one of these settings, you should really think of the tangent space as being HM. And when you're in these exceptional cases, somehow your tangent space has to do with the Arctonians. In this case, your tangent space looks like the imaginary Arctonians. I'll explain what that is in a minute. And in this case, your tangent space looks like just the Arctonian algebra. So, so there are well-known relationships between holonomy on the one hand and calibrations on the other. Indeed, in their paper on calibrated geometry, Harvey and Lawson in 1982, when they found the subject of calibrated geometry, they point out these basic examples of calibrations, and their examples, as I'm going to explain in a minute, are these, right? They're examples that come from having reduced holonomy in the Kähler, Calabi-Yau, G2 and spin 7 settings. It's somewhat interesting, just sort of historically, that the examples that Harvey and Lawson provided us in that paper were sort of the complex and octonionic ones. They sort of skipped over the quaternionic ones. Those were, treated in a later paper of Bryant and Harvey that unfortunately has not been nearly as widely read. And I want to encourage people who are interested in calibrated geometry to read both papers, that of Harvey and Lawson, and also that of Bryant and Harvey for the story in the hyperkähler setting. As a graduate student, I was under the misconception that because Harvey and Lawson didn't mention the quaternionic case, that maybe there weren't any interesting calibrations in the hyperkähler world. But in fact, the opposite is true. There's so many calibrations in the hyperkähler setting that it's actually overwhelming. In my opinion, there's a huge amount of work that one could do and that one ought to do about calibrated geometry in the hyperkähler setting. There's sort of a lot of really basic things we don't know, which makes it very exciting. And that there has not been nearly as much work on this that as I think deserves, in my opinion. Okay, but I haven't told you what any of these forms are, so let me explain what these forms are. I'll explain what these forms are in the context of Euclidean space, because that's the context that's relevant for us. These forms make sense more generally in the Kähler, Calabi-Yau, etc. settings, but I'm going to explain them in the Euclidean context. Okay, so everyone's first example of a calibration usually is the Kähler form. So let's let M be R2M. Okay, and I'm going to think of R2M as CM. I'm going to have coordinates Z1 through ZM. Okay, and the standard Kähler form is this 2 form here. Okay, dx1 wedge dy1 up to dxm wedge dym. And that's omega. And from omega, we can take sort of these normalized powers, 1 over p factorial times omega to the p. Okay, and it turns out that these 2p forms are calibrations. And moreover, the submanifolds that they calibrate are precisely the complex submanifolds. Okay, and using these 2 facts, we deduce Vertinger's theorem as a corollary of Harvey and Lawson's fundamental theorem on calibrations. Complex submanifolds in R2M, consequently, are area minimizing in their homology class. Okay, the sort of second example of calibrations that one typically learns about are the special Lagrangian calibrations. So again, we're working in CM. We'll fix a unit complex number, e to the I theta, called the phase, and we'll define the following M form. Okay, so this is an M form in R2M. The special Lagrangian M form of phase e to the I theta is this right here. It's the real part of e to the negative I theta, dz1 up to dzm. Conventions differ. I put a minus sign here, as I think most people do, but some people don't put the minus sign. Harvey and Lawson in their paper showed that upsilon sub theta, all of them are calibrations, and their calibrated submanifolds are called special Lagrangian of phase e to the I theta. Okay, so by the fundamental theorem of calibrations, special Lagrangians are area minimizing in their homology class. You might wonder why they're called special Lagrangians. They don't a priori seem to have anything to do with special Lagrangians, but in fact, it turns out that being special Lagrangian of phase plus or minus 1 for simplicity, the phase in most, not but not all, but in most contexts is not very important. Being special Lagrangian of phase plus or minus 1 is equivalent to being Lagrangian and also satisfying this additional condition here. So special Lagrangians are indeed Lagrangian, but there's another condition which also has to be satisfied in order to be special Lagrangian. I didn't put this on the slide, but one can also prove this is also in Harvey and Lawson. if I recall correctly, that special Lagrangians in Euclidean space, special Lagrangians are precisely those Lagrangians that are minimal, right? So being minimal Lagrangian is equivalent to being special Lagrangian of some phase in Euclidean space, and I think more generally in any Calabi-Yau manifold. Okay, so these are somehow the basic calibrations in even dimensional Euclidean spaces. What of these sort of exotic calibrations in dimension 7 and 8? So for that, let me briefly recall what the octonions are. The octonions are, of course, the norm division algebra that's not RC or H. By Hurwitz's theorem, there's only 4 norm division algebras, RC, H, and O. Of course, this definition is not very helpful to anyone. More seriously, the octonions can be viewed as pairs of quaternions with the following multiplication law. So this is similar to how we define complex numbers as pairs of real numbers. Okay, and this is perfectly fine, but maybe not really the best for many computations. For computations, you really need a basis. So here's yet another way of defining the octonions. This is the way that I prefer for computations. Octonions, for me, are objects that look like this. They're objects that can be written x0 plus x1e1 plus x7e7, where the xj's are real numbers. And I can add them in the obvious way and scale them in the obvious way. What's not obvious is how you multiply them. You multiply them by requiring R bilinearity and the following multiplication table. Also, EI squared has to be -1. EI EJ is negative EJ EI for I not equal to J. This can be summarized in this multiplication table here. I put the colors to sort of emphasize certain patterns that are in fact quite important in the study of these octonionic calibrations, right? I want to point out that E1, E2, E3 times E1, E2, E3 returns an element of E1, E2, E3, whereas 4, 5, 6, 7 times 4, 5, 6, 7 returns an element of, 1 E1, E2, E3. So that's sort of the opposite sort of thing going on here. Meanwhile, if you mix up E1, E2, E3 and 4, 5, 6, 7, you get something back in 4, 5, 6, 7. Okay, there's sort of an even and odd thing going on here, if you like. Okay, so using the octonions, we can explain what these sort of exotic or exceptional calibrations are in R7 and R8. So thinking of R7 as the so-called imaginary octonions, by which I mean the span of E1 through E7, we can define the famous 7-dimensional cross product like so. Remember, octonionic multiplication is not commutative, so this makes sense. This is not 0. And this is a cross product in the sense that it's skew symmetric. U cross V is orthogonal to U. It's also orthogonal to V, and it has the norm that you think it does. It turns out that they're the only cross products, the only bilinear maps that have this property. There's one in dimension 3, of course, the familiar one, and there's one in dimension 7, and that's it. Anyway, using this 7-dimensional cross product, we can define a 3 form in R7 like so. Here, the inner product is the standard inner product in R7. And moreover, we can take the Hodge star, that's the standard Hodge star in R7, and define this 4 form. So these are the associative 3 form and the co-associative 4 form. In the standard basis, they look like this. Here, when I write E1, 2, 3, I mean E1, wedge E2, wedge E3. Sort of scary looking expressions here. You'll notice that the components for phi, this is the octonionic multiplication table again. E1 times E2 is E3, E1 times E4 is E5, etc. And the point here is that this was shown by Harvey and Lawson. Both phi and psi are in fact calibrations. They are closed and have comass 1. The 3-dimensional submanifolds in R7 that are calibrated by phi are called associative. And you might wonder why they're called associative. They're called associative because they have the following property. If you have a 3-dimensional submanifold that's calibrated by phi, then the tangent spaces have a basis that is associative. You can find a basis for the tangent space for which the multiplication is associative. Interestingly, associatives are also those for which those submanifolds for which the tangent space is closed under the cross product. That is somehow formally similar to how complex submanifolds work, complex submanifolds are those whose tangent spaces are invariant under J. And indeed, associatives are in a very, in many ways, somehow formally analogous to complex curves. That analogy is a very important one in the study of associatives, but that's maybe for another day. Similarly, of course, co-associative fourfolds in R7 are those which are calibrated by the co-associative four-form. They can equivalently be characterized as those for which, if I take two tangent vectors, their cross product is normal. So which sort of makes them kind of like Lagrangians in a way. Co-associatives are in some sense very similar to special Lagrangians, in fact, and that's a very important analogy. They can also be defined as those for which the three form vanishes. Okay, so these are some important characterizations of associatives and co-associatives. And finally, the other kind of remaining fundamental calibration in Harvey and Lawson's paper is in R8. Here we're thinking of R8 again as the octonions. You can define this triple cross product like so. Again, remembering that octonionic multiplication is neither commutative nor associative. Okay, and again, it's a theorem that just like ordinary cross products can only occur in dimensions 3 and 7, triple cross products can only occur in dimensions 4 and 8. That's a theorem of Brown and Gray. Anyway, using this 8-dimensional triple cross product, one can write down sort of the analog of the associative 3-form. This is the so-called Cayley 4-form, defined very similarly. And in the standard basis, it looks like this. And Harvey and Lawson prove, again, that this 4-form, well, it's closed, but it has comass 1 is the surprising thing. And again, we can say that a 4-dimensional submanifold is Cayley if it's calibrated by, well, the Cayley 4-form. So again, Cayley submanifolds by the fundamental theorem of calibrations are area minimizing in their homology class. Okay, so these are the basic calibrations in geometries associated to the complex numbers and the octonions. There are so many more calibrations in R4N associated to the quaternions, which maybe I'll mention some of those next time. Okay, so in closing, I want to mention how what I just said relates to the next lecture, just to sort of set up what it is we're going to do in the next lecture and sort of explain kind of the philosophy. So, what we've been doing in this part of the talk and the last part of the talk, we've really been viewing Euclidean space as having extra geometric structure, right? I mean, when we talk about the standard Kähler form on R2M, for example, we're really thinking of R2M as a Kähler manifold. When we talk about the special Lagrangian form on R2M, we're thinking of R2M as sort of a trivial Calabi-Yau manifold or the tangent space to such. Similarly, when we think of R7 as the imaginary octonions, we're thinking of it as a trivial sort of flat G2 manifold. So even though we're working in Euclidean space and you can say Euclidean space is boring, really Euclidean space is the space that admits, any geometric structure you want, more or less, and that's really the correct perspective to have. And the point is that when we have this extra geometric structure, we get special classes of minimal submanifolds, namely the calibrated ones I just mentioned. But since we have this extra geometric structure on Euclidean space, that induces special geometric structure on the unit sphere, right? So, you can view, for example, the 2n+1 sphere not just as the round sphere, but you can view it as a Sasaki-Einstein manifold, right? In other words, as the link of a Kähler manifold. Similarly, the 4n+3 sphere, you can view it as a 3-Sasakian manifold. S6 is nearly Kähler, and S7 is nearly parallel. Those words are not so important. If you don't know what nearly Kähler or nearly parallel means, it doesn't matter. The important thing to note is that certain spheres are quite special in the sense that they have extra geometric structure arising from the corresponding structure on their Euclidean cones. Accordingly, what that means is that just as these Euclidean spaces that we've discussed have these sort of distinguished submanifolds, the calibrated ones, complex, special Lagrangian, associative, co-associative, and Cayley, it follows that their Euclidean spheres have distinguished submanifolds as well. CR, special Legendrian, holomorphic curves, Legendrians, and associatives, and these will be the subject of next lecture. The point is that these are submanifolds that satisfy first order PDE that automatically imply the minimal submanifold system. So all of these sort of special submanifolds of spheres are in fact minimal. And these sort of, I think, in my opinion, are the most fundamental minimal submanifolds of high codimension in spheres, and are sort of, I think, worthy of a lot of study. So we will discuss these submanifolds here in round spheres in the next lecture. I'll discuss some problems relating to the index. Yeah, so I'll see you next time. Thanks.
All right, thank you very much. Any question? All right, thank you very much for this nice, interesting talk.